All right, take two. If the cat will allow me, I'm going to tell you all about torque. Now, torque is analogous to force. So it turns out the things we've been studying about rotational motion, each thing we've talked about has an analogy with linear motion. For example, in linear motion, we talk about the position of an object, x. If we take the time derivative of x, we get the velocity v. If we take the time derivative of that, we get the acceleration a. Well, if something's rotating, I can describe how far it's rotated with an angle theta. If I take the time derivative of that, I get omega, the angular velocity. Time derivative of that, I get alpha, the angular acceleration. And the distance that something moves as it rotates, so if I have some rotating object and I look at some point on that object, the distance that point moves is just r, the distance from the center of rotation to that point, times theta. Take the derivative of that, and the linear velocity is then related to the angular velocity, and the linear acceleration is related to the angular acceleration. All right, so you'll recall when we started talking about angular motion, we had this figure here, and we said we could describe how far something has rotated with an angle theta. Again, if we take the derivative of that with time, we get omega, the angular velocity. If we find how omega changes with time, we get alpha, the angular acceleration. Now, if I take a point on my object, when that object rotates a distance theta, that point moves a distance s, which is simply given by r times theta. It's just the length of the arc. And if I take the derivative of that, I'm going to get the velocity, so the tangential velocity of that object. And that is just then the linear velocity is r times omega. Same thing with acceleration. Okay, we also found that angular displacement, angular velocity, and angular acceleration are vectors. And we described how we could use the right-hand rule to understand the direction of these different parameters. For example, if I have a tire that's going to the right, I curl my fingers in the direction that the tire is rotating, and if I'm using my right hand, as I should, to do the right-hand rule, my thumb will point in the direction of the angular velocity. If the tire is going the other way, I take my right hand, I curl my fingers in the direction that the tire is rotating, and my thumb shows me the direction of the angular velocity, in this case pointing outward. We also talked about moment of inertia, I. And moment of inertia is analogous to mass for linear motion. We came up with equations. I gave you equations to calculate the moment of inertia. So for example, if we had discrete masses, we use this equation here where we just sum up each mass times the distance from the axis of rotation to that mass squared. If we had a continuous distribution of mass, this sum turned into an integral where we would break up our continuous distribution into little pieces of mass of size dm, and then we just integrated r squared, the distance from the axis of rotation to that little piece of mass dm squared. We just integrate r squared with respect to dm to get the moment of inertia. And as you'll recall, we decided that the moment of inertia, unlike mass, which is just mass, right? The moment of inertia depends on the direction of the axis of rotation. We decided that wiggling barbells this way, you'd have a different moment of inertia than if we just rotate them back and forth. We also decided that even for a given direction of our axis of rotation, the moment of inertia also depends on the location of the axis. We decided that the moment of inertia for doing this type of rotation about this axis was different than the moment of inertia about this axis. We also decided that the moment of inertia depends on how the weight is distributed relative to the axis. Okay, so that's the end of our review. Now we're going to talk about torque. Torque is the rotational analog to force. And it turns out that you can find the torque caused by a force simply by taking the cross product of the lever arm with the force. And we'll talk about what the lever arm is in just a moment. But first I want to point out that Newton's second law also applies to things that are rotating. So for linear motion, force equals mass times acceleration. So force is the thing that causes acceleration, and mass is the inertial thing that limits how much the acceleration changes for a given force, or how much acceleration there is for a given force. In rotational motion, we have torque equals moment of inertia times angular acceleration. So torque is the thing that causes things to have angular acceleration, and the moment of inertia is the inertial property which limits how much angular acceleration you get for a given amount of torque. And once again, we can calculate torque by taking the cross product of the lever arm with the force. Okay, so imagine I have a bar with a mass on it, and I'm applying a force right here. What torque does that force produce? Well, the lever arm, R, is simply the distance from the pivot point out to the point where we apply the force. All right? And so we just take the cross product of that lever arm with the force, and we get the torque. In this case, the two of them are at 90 degrees to each other, right? And as you recall, if you've forgotten all about cross products, you might want to go back and review the video where we talked about vectors. But if you recall, the magnitude of R cross F is just the magnitude of R times the magnitude of F times sine of the angle between them. In this case, the angle between them is 90 degrees. And so the magnitude of the torque is just R times F. And so our torque vector is just RF times K hat. So RF in the z direction. How do I know that the torque is in the z direction? Well, I use the right-hand rule, right? To find the direction I get with a cross product, I start with my fingers pointing in the direction of R, with my palm in the direction such that as we move towards the direction of the force, I'm going to move palmward. So then I take my palm and I rotate my hand into the direction of F, and that gives me the direction of my torque, which is in this case the z direction. All right, now the lever arm, R. The magnitude of the torque is proportional to the lever arm. So if I shorten the lever arm, the magnitude of the torque goes down. Bigger lever arm, bigger torque. Smaller lever arm, smaller magnitude of torque. And this is something you should have experience with. You go to open a door. You go to push open a door. If you push close to the hinges, it's really hard to open a door. But if you push far away from the hinges, such that you have a big lever arm, then it's not as hard to open the door. The angle of the force also affects the torque that is produced. All right, so imagine I'm pushing on this rod with a force, with a lever arm of R. What happens if I change the angle, move it away from 90 degrees? Well, remember, the magnitude of the torque is RF sine theta. So as theta moves away from 90 degrees, the torque is going to go down, right? So if I change my angle to some angle theta, then the torque goes down. Now, the right-hand rule will once again tell me the direction of the torque. And I just take my fingers, put them in the direction of R, rotate my palm to go into the direction of F, and my thumb then points in the direction of the torque. And the torque, in this case, is still in the z direction. So my torque is RF sine of theta in the z direction. All right, now once again, now we know how to calculate torque. Torque is the thing that causes angular acceleration. So we can use that now to work a problem. A rocket engine of negligible mass is attached to the end of a 2-meter-long rod of negligible mass at an angle of theta equals 55 degrees. The other end of the rod is attached to a massless, frictionless pivot point. Halfway between the two, a point mass with a mass of 10 kilograms is attached to the rod. If the rod is initially motionless and the rocket produces a constant force of 50 newtons, how far will the rod turn in 10 seconds? Ignore gravity and friction. Well, the first thing we need to address is that there's too many thetas in this problem, all right? So there's the theta here that we've defined that gives us the angle of the rocket force relative to the bar. But of course, we usually also use theta to describe how far something's rotated. And then there's a theta between, and the angle between the lever arm and the force that's going to come up as well. So we basically have three things that we have been calling theta. So we're going to make up some different names here. So I'm going to use phi to represent how far the thing has rotated. And of course, it's going to rotate downward, so the displacement of phi will be in the negative z direction. Okay, if I have a constant force with a constant lever arm, that's going to produce a constant torque. All right, so I'm going to have, just in analogy with equations of constant acceleration, remember we have our equations of constant angular acceleration, where we say the final angle equals the initial angle plus the initial velocity times the initial angular velocity times time plus 1/2 angular acceleration times t squared. In this problem, we're starting off with no angular velocity at time t equals 0. So the change in theta, or the change in angle, which we're calling phi because we're already using theta for something else, is just going to be 1/2 angular acceleration times t squared. We're given the time, so we just need to find the angular acceleration. Well, we get that from Newton's second law. Torque equals I alpha. Torque equals moment of inertia times angular acceleration. So that means angular acceleration is just the torque divided by the moment of inertia. Well, the moment of inertia is easy because there's only one thing with non-negligible mass in this problem, and it's got a mass that's given, and we know that its position, it's halfway along the rod. So the distance from the mass to the center of rotation, to the axis of rotation, is just the length of the rod over 2. So the moment of inertia is just m times L over 2 squared, mr squared. And then the torque we get from the force. If we look back here at our drawing, we have a force that's given, that's going in a certain direction, and the lever arm for that force is just the length of the rod. So that means the torque is just going to be the length of the rod times the force given times sine of theta, where theta is the angle between the lever arm and the force. Well, if we look at this drawing here, we've used theta to represent this angle right here. But the angle between the force and the lever arm is really that angle right there, right? If I put my fingers in the direction of R and rotate them until they're in the direction of the force, this is the path that my hand will take. So the angle between the lever arm and the force is really 180 degrees minus theta. So our torque is really LF times the sine of 180 degrees minus theta. Well, it turns out that the sine of 180 degrees minus theta is the same as the sine of theta. You can think about that, draw some pictures and figure that out. But just for the sake of being correct, technically correct, I'm just going to leave it as 180 degrees minus theta for right now. So the change in angle is 1/2 alpha t squared, and alpha is just the torque divided by the moment of inertia. And I've taken away the vector sign. We're just going to find the magnitude, and then we know it's going to go in the clockwise direction. All right, and so the torque is just LF sine of 180 degrees minus theta, and the moment of inertia is just m times L over 2 squared. Then we can simplify that a little bit, and then we plug in our numbers, and we get our answer, which is 410 radians, or 2.35 times 10 to the 4th degrees, which is also 65 rotations plus 67 degrees. So it's 65 complete rotations plus 67 more degrees. Now let's talk about how you find the torque due to gravity. It turns out when you're calculating torque due to gravity, gravity acts as though all of the mass is concentrated at the center of mass. So you can pretend like gravity is just a force acting at a point, and that point is at the center of mass when you're calculating torque. Now, I'll explain why that works out in a minute. For now, let's just run with it. So let's use that to work a problem. A thin uniform board with a length of 3 meters and a mass of 2 kilograms is placed on top of 2 tall narrow bricks with rounded tops. One of the bricks is 25 centimeters from one end of the board. What is the magnitude of the torque due to gravity about the point of contact with that brick? Well, we're going to find the torque. Torque is just RF sine theta. And we're going to pretend like the force due to gravity is all concentrated at the center of mass of our board, halfway between the ends of our board. Well, the angle of gravity relative to the lever arm is 90 degrees. And of course, the force, the magnitude of the force is m times g. So now we just need to find the lever arm. Well, the center of mass is L over 2, the length of the board divided by 2 away from the end close to our pivot point. And the pivot point is a distance I'll call x in from the end of the board. So that means that the lever arm is just the distance from the brick, from where the brick touches the board, to the center of mass from our board, and that's just the length of the board over 2 minus x. So that means the torque is just L over 2 minus x times mg. And we can just take that and plug in numbers, and we get 24.5 Newton meters. Now, why would you want to know the torque of the board, of gravity on the board about a particular brick? Now, note, the torque you get is different depending on which brick, right? Depending on where you place your rotation axis. But why would I want to know that? Well, we're going to find that out later. Not in this video, but in a future video. All right, now here's another cool thing about torque. Here's another principle you should know about. So if I have some force that is acting at some angle on a bar or on some object with some lever arm, the torque, the magnitude of the torque is just R times force times the sine of theta. But there's another way we can write this. So imagine I draw a line from the pivot, from the axis of rotation, out such that it hits this dotted line, which is extending the direction of the force, such that it hits that line at 90 degrees, like that. Well, notice that this angle, if this angle here is theta, this angle right here is 180 degrees minus theta, which means the length of this line right there is r times the sine of 180 degrees minus theta. And the sine of 180 degrees minus theta is the same as the sine of theta. So the length of that line right there is just r sine theta. We will call that line the perpendicular distance. So the torque is RF sine theta. The magnitude of the torque is RF sine theta, but it's also equal to the perpendicular distance times F. All right, so one way to find the magnitude of the torque is you take R, F, and then multiply by sine of the angle as you go from R to F. But another way you can do it is you can draw a line that is basically in the direction of the force that intersects our object where the force is being applied to our object, draw a line that goes from the pivot point to the force line, which is perpendicular to the force line. That distance we call r perpendicular, and knowing r perpendicular, the magnitude of the torque is just r perpendicular times the force. Okay, one last thing to explain before we're done. I just wanted to, you can just say, hey, look, the torque due to gravity, it acts like all of the mass is concentrated at the center of mass. But I just wanted to, in case you're interested, explain why that is true very quickly before we end this video. So imagine I just have some random blob, and I want to know what is the torque due to gravity on this blob about the axis shown in red. Well, the way I'm going to do that is I'm going to break my blob up into little tiny cubes, all right? And each cube has a little mass, which is the density times the width times the height times the thickness of that little cube, all right? Well, the torque on my object due to gravity is just the sum of the torque of gravity on each little cube, in the limit as I have an infinite number of infinitesimal cubes. Well, let's just consider one of these cubes. This cube has a lever arm R, and then it's got gravity, a force due to gravity, pulling on it. Well, the torque is just R, the lever arm crossed in the force due to gravity. But the force due to gravity on this little infinitesimal piece is just the direction of g, right? The vector g, so magnitude of acceleration in the downward direction, times mass, right? The force due to gravity is mass times g. Here, g has a direction, and the mass is just the little infinitesimal mass of that little cube right there. Well, notice this vector right here, that's just x. And x, since gravity is in the negative y direction, x is just going to be the perpendicular distance of our little piece of mass. So remember, we can find torque by taking the magnitude of torque by r f sine theta, or just r perpendicular times the force. And so we know that the torque due to gravity from this piece is going to produce a torque in the negative z direction. So I'll just write negative k hat and then calculate the magnitude of the torque. But the magnitude of the torque is just the perpendicular distance, which happens to be x, times g times dm. Well, notice g is a constant. It can come out of our integral, and what we're left with is the integral of x times a little bit of mass. And you know what that is? That is just the x component of the center of mass. All right? So the torque due to gravity is just mg times the x component of the center of mass times the direction. All right? So wherever the center of mass is, all right, it can have a y component, but the y component doesn't matter because the y does not change the perpendicular distance. It can have a z component, but translating mass along the axis doesn't change torque. So all that matters is just x. So if I can pretend like all of the mass is at some x location, which is equal to this x component of the center of mass, then that tells me I can just, when calculating torque due to gravity, I can pretend like all of the mass is just at the center of mass location. And that's the end of today's discussion.